Okay, we're now going to talk about the part of a project where we addressed climate-based daylight metrics. And once again, I'm going to kick off and then pass over to Cosmin later on. Climate-based daylight metrics, including the daylight autonomy and useful daylight illuminance, are based around a yearly simulation of daylight. And the idea is that you calculate daylight on a time step basis. So you'd start at, I suppose, sunrise on the 1st of January, and you'd carry on maybe every 15 minutes throughout the year, and you'd do a daylight calculation for each of those. And the way that daylight calculation is done is, first of all, to obtain basic climate data from a weather tape. And usually that would be in the form of irradiances, maybe global and diffuse irradiance. And then it's possible to convert those to illuminances. So just sort of revision here. The irradiance is the total solar spectrum, so it's the solar gain, whereas illuminance is obviously what your eye can see. So, and there's conversion factors called luminous efficacy, which allows you to convert irradiances into illuminances. And then you get an outdoor illuminance. But to work out the daylight indoors at a particular time, you also need what's called the sky luminance distribution, and that's the brightness pattern of the sky. So under an overcast sky, you get one sort of brightness pattern. Under a clear sky, you get a very different sort of brightness pattern, which is brighter nearer the sun, and it's also brighter at the horizon than an overcast sky is. And under a partly cloudy sky, you get quite a random and exciting luminance pattern. And those people who are in the cheap seats right at the very back will be able to stare out a window when I get to the boring bits of my talk, and they'll be able to see such a partly cloudy luminance pattern. And they'll see that it's not quite as simple as the equations predict. And one of these, this is how you actually get this sky luminance distribution is almost magical, because you start off just from two pieces of data, which are the global and diffuse irradiance, and from that you try and predict whether it's going to be sunny or not, and from that you try and predict whether what the sky luminance pattern is like, and whether it's going to be brighter nearer the sun, or whether it's going to be more like an overcast sky pattern. And also, depending what sort of weather tape you're using, it may well be that the people who develop a weather tape, they didn't actually use measured global and diffuse irradiances at all. They actually calculated them from something else, and maybe they calculated the diffuse from the global. And so you've generated a sky luminance distribution more or less out of thin air. And people, when they're doing this climate-based daylight modelling, they tend to believe the results quite, and thinking, oh, well, this illuminance here, this is, they quote them to lots and lots of significant figures. Whereas in reality, a lot of this stuff is guesswork, very educated guesswork, and clever people have done a lot on this. But it's still essentially guesswork. Anyway, when you've got your sky luminance distribution, then you can use something like radiance to calculate internal illuminances on a grid covering the working plane. And this is usually used, these illuminances on this grid is what's usually used in a climate-based daylight metric model. And what that generates is an awful lot of numbers. We were talking about a 15-minute time step earlier, and if you work that out, that's 18,000 separate daylight calculations over the whole year. So there's 18,000 instances when you've got to do all these first four things and calculate the daylight. And then maybe you've got, say, even quite a coarse grid on your working plane. Say you've got a 10 by 10 grid, that gives you 100 points. And so that will generate 1.8 million numbers compared to our one number, which was the average daylight factor. And so what you then need to do is you then need to do post-processing of those 1.8 million numbers in order to give you one or two numbers which you're going to be using as your climate-based daylight modelling parameter. So effectively, you generate all these numbers, and then you have to condense them back down into one or two single useful numbers, because otherwise the people you're presenting these numbers to won't have a clue what's going on. So the first of these numbers is the daylight autonomy. And the daylight autonomy is the proportion of the year for which a given target daylight illuminance is exceeded. And often 300 lux is used as a basis for this, because it's a typical lighting level in a school or office, something like that. And we're going to be referring quite a lot to the Education Funding Agency, because this is in the UK, this is the first organisation to actually require climate-based daylight metrics as part of its specification. So new schools have to meet these Education Funding Agency requirements. And one of the things it requires is a particular daylight autonomy. And if you look at it, this is 50% daylight autonomy. So that means the daylight has to exceed 300 lux for more than 50% of the time, over 50% of the working plane. So what that means is, essentially this means that the daylight in the middle somewhere has to exceed 300 lux over 50% of the, in this case, a school year, during a 8:30 to 4 o'clock year, which corresponds to the typical school day, which is a perfectly reasonable thing, given that we're talking about schools. The daylight autonomy could be linked to perhaps when you might need to switch your electric lighting on. So suppose you switch your electric lighting on when the daylight in the middle of the room was 300 lux. Then the daylight autonomy would be roughly equal to 100% minus the lighting use in the space. Now, daylight autonomies can vary according to the different parameters. Obviously, you could have a different percent daylight autonomy, so you might require 300 lux to be met more than 50% of the time. And you could have a different proportion of a working plane, so you might say, well, it has to be over more than 50% of a working plane. And also, you can have a different year over which you do the assessment, and this can make a lot of difference. And if we look at the proposed European daylight standard, and this standard is not actually at the sort of published draft stage. At the moment, there's a committee being formed at a European level, and this is the sort of thing they've sort of taken over from an earlier committee which came up with this draft, and so this is just an initial proposal at this stage. But what the initial proposal says, it gives what appears to be a very similar daylight autonomy guideline. It requires 300 lux for over 50% of daylight hours, over 50% of a working plane. So can you spot the difference between that and the Education Funding Agency? Correct. Yeah, instead of using school hours, which is just 8:30 till 4 o'clock, we're using daylight hours, which in the summer could be, say, from 5 o'clock in the morning up to 7 o'clock at night, or or perhaps if we're using British summer time, it could be 4 o'clock in the morning. No, hang on, 6 o'clock in the morning up to 8 o'clock at night. So, the European standard, although it looks very similar, is actually stricter. It's quite a lot stricter. In fact, we worked out it's 34% stricter. Yeah.
In defining the working plane, can you subtract areas right at the back of the classroom, the education funding agency?
Yes, you can, and we've got a slide about that later on. The European standard also recommends additional recommendations, which is that you should get 100% of a working plane, so that's a whole room, should have 100 lux for at least 50% of daylight hours. And obviously, depending on the obstructions you've got outside and the depth of your room, this could be a very difficult thing to achieve. And these two recommendations are just the minimum values in the European standard. As well, it gives further recommendations for medium daylighting and high daylighting, which are actually quite a lot more. So for high daylighting, you're supposed to have 750 lux, over 50% of the working plane for 50% of daylight hours. And then 500 lux over the whole of the working plane for 50% of daylight hours. So that's quite a difficult thing to achieve in a daylit space. And just to make it a bit more complicated, the guidance in America, which is given in the IAS of North America publication LM 8312, that gives a thing called Spatial Daylight Autonomy, which essentially means it's sort of similar but different. So what it says is that for preferred daylight sufficiency, you should have 75% of your working plane exceeding this 300 lux for more than 50% of in this case, 8 till 6 working day, which theirs is really targeted at offices, and it's based on a study that was done in offices. And for nominally accepted daylight sufficiency, they say 55% of a working plane should exceed this 300 lux for more than 50% of this working day. And if you take the nominally accepted value, it's likely to be stricter than the Education Funding Agency guidance, but less strict than the European standard. The other criterion, which is often used as a climate-based daylight metric, is useful daylight illuminance. And this is sort of related to the daylight autonomy in that to count, the daylight has to be above a certain value. But also, for useful daylight illuminance, it also has to be below a certain much larger value. And so the daylight has to fall within a useful range. And often, say, something like 100 to 3,000 lux is used. So the idea is that if the daylight's really high, then people will think, oh, it's far too bright in here, let's put the blinds down. And then the daylight isn't really going to be useful anymore. So that's the idea behind it. So the idea is that too much daylight is as useless as too little. And this 100 to 3,000 lux range is what's used in the Education Funding Agency guidance, or requirements, and it requires this for an average of 80% of a school year. Again, it's done over a school year. And what you do is you calculate this for each point within the school classroom or whatever it is, and then each of those points has a percentage which is for useful daylight illuminance. You think It's a bit confusing, useful daylight illuminance, because you imagine it should be in lux because it's an illuminance, but actually it's in percent. It's the percentage of the year that the illuminance falls in this useful range. And you calculate that at each point. And so for points at the back, you might get a lower value because more likely to get low illuminances. And maybe for points near the window, you might also get a lower value because they're more likely to get these very high light levels. And then for points in the middle, you might get 100%. And then you average all of these, and then you compare that to 80%. And if it's more than 80%, then you can build your school classroom. The European standard doesn't give a UDI recommendation.
So what happens if it's too bright at the perimeter, so the light comes down, but you're looking at a point in the middle of the room, that assumes the blind is left open for the available?
Well, no, you shouldn't do that. No, that would be cheating. No, you've got to have the same shading condition for each point in the room. So if you brought the blinds down, you've got to calculate the whole room like that, and so obviously you might get a lower UDI at the back of the room.
Perimeter triggers the blinds coming down, and therefore obscures the whole of the room.
Yeah, well, it would. Yeah, I think that's fair, isn't it? Because that's what would happen in practice.
The spreadsheet just keeled over and collapsed.
No, well, you can't do this using a spreadsheet. I mean, because you've got 1.8 million numbers in here, your spreadsheet would have given that a ghost age. Well, if you got a computer like mine, it would have done.
Sorry. The European standard, is that the TC 169?
No, sorry, this draft European standard I was talking about.
Oh, in the new, okay.
Yeah, well, it's not even new. It's sort of to be published sometime in the indefinite future.
Because the one I was aware of was talking about modified daylight factor that was based on accumulative values from the weather file and giving more or less the same definition, but it was like a modified daylight factor rather than daylight autonomy.
Yeah, and I think they've moved on in drafting it. So the latest one I've seen, which was sort of early 2015, that included the daylight autonomy. I don't know if they actually call it daylight autonomy or whether they just say it's got to exceed this value for a particular fraction of the year. But effectively, it is a daylight autonomy. Yeah, and again, there's more complicated ones, and John Medalievich would explain this a lot better than me. But essentially, it's possible to divide the UDI into different categories. And this can be a useful thing. If you're trying to work out whether your daylight isn't useful because it's too low, or because it's too high, because then you can, obviously if it's too high, you could introduce more shading. If it's too low, you could introduce more glazing. So this is quite a useful thing to be able to do. So you have different categories of UDI. So you have like UDI F, which is UDI fell short, where the daylight's too low. And then you have UDI S, where the daylight's quite low, but it's probably enough to do something. And then you have UDI A, which stands for UDI autonomous, like daylight autonomy, where the daylight is really enough to be used as a sole illuminant. And then you have UDI E, where the daylight's too much. So you've got too high levels. And what you can do is you can work this out for each point. And you can say, well, you know, at these points, daylight is too much for quite a lot of the year. And you can also do it as an average over a whole room. And you can think, well, you know, this room really has a poor UDI because it's actually got too much daylight. And if we got rid of some of it, it would be, we might increase the UDI.
Let me interrupt you, but I think it's useful to have a differentiation between too much diffuse light, which has effects on, for instance, screen visibility, and the presence of direct beam sunlight. And the beauty of this tool, I call it the beauty, is that you can start to differentiate that and understand the importance of orientation, size of windows in the building. which the other methods do not permit directly. And it also shows up, and that brings me back to my question about the Lenny area, is that the assumptions based in Lenny do not take into account the sunlight penetration into interiors. As a result, endow it with a degree of uncertainty, which I think we have to be cautious about.
Yeah, I agree wholeheartedly with your second assertion. I'm not sure about the first one though, because the 3,000 lux, that's 3,000 lux from anything. So it could just be because you were...
You can change the numbers very easily and determine which areas you're going to receive direct sunlight. The point about this is that the parameters are used by set by the user. The areas which are in a sense of most interest to us in terms of daylight autonomy are simply the areas where we spare ourselves the use of electric lighting. So there are two different things going on simultaneously here, and that's where the power of this type of tool is starting to allow us to look at building design in a rather different way.
Well, again, I agree with the last thing, but I mean, it doesn't actually. I think I understand the point you're making. I mean, say if we just took 3,000 lux, the UDI reacts to that. If we're using 3,000 lux, it doesn't actually matter whether it's diffuse or because perhaps you're really close to a window on a bright day, or whether it's 3,000 lux because the sun's shining on it. Usually it would be because the sun's shining on it. I agree you could take a higher illuminance and maybe that would isolate out the times when sun was shining on your particular point. Although that's not always the best metric of glare, because sometimes the glare, it might not be whether the sun's shining on the working plane, or whether it's shining in your eyes or on your computer screen. So I guess, yeah. But I mean, I think you're right in that what it does is it tells us that we've got too much, which the daylight factor never did. It always is, and you'd always be thinking, oh, well, I've got to meet this particular daylight factor, so you could chuck glazing at a problem, and then you get into this sort of area where perhaps you get a room which was equally unsatisfactory, but because of sunlight and glare rather than because of lack of daylight. Sorry, Joe, did you have a...
Well, I was going to make precisely the point which you've just made, that glare doesn't depend on the illuminance and the horizontal plane. When we're dealing with artificial light and the glare index, we don't attempt to relate that to horizontal illuminance, and it's quite stupid to do it for daylight.
Okay, yeah. Okay, thank you. I mean, perhaps now would be a good time to flag our next but one meeting where we're going to be talking in a lot more detail about climate-based daylight metrics, and I think John Medalievich will be here to either defend UDI or possibly agree with you. I don't know. I don't want to preempt what he might say. Yeah. So actually, yeah. So I've written the right thing on my slide. High illuminance is not necessarily the best measure of glare. And there's an interesting study, and most of you aren't aware of this study. This is a really good thing you can download this free of charge from the internet. This is a study called PEER, which PEER stands for something. It's not actually sort of seaside piers. It actually stands for, which I can't remember what it stands for, but maybe the illuminance, I is illuminance, or something like that. But anyway, you can download this, and they did a really detailed survey of 61 offices and classrooms. And one of the things they found was that no level of annual daylight illuminance was found to be too high. And so for that reason, the IES doesn't have a useful daylight illuminance metric either. Now, the peer studies methodology has been criticised. One of the things was they actually did the study in July and August in California, when the sun's usually really high in the sky, and so you're much less likely to get penetration of sunlight into interiors. So maybe it's more different here where you're likely to get low angle sun coming in. And the other thing is that the useful daylight luminance is often related to things like schools and offices, but again, as I was saying right at the start, most daylight calculations are done for dwellings. And in residential buildings, people often welcome sunlight. And in tests, 90% of people said they preferred sunlight. And so obviously, useful daylight illuminance in that sort of situation is probably a less appropriate metric. One of the most interesting things we did in the project was we had a little workshop, actually a couple of workshops with daylight consultants who actually used UDI in the design of schools to meet the Education Funding Agency requirements. And it was quite interesting to find their actual experiences with using the metric. And I don't think any of them are here, was there? No. None of them are here, but so I hope I've represented their views correctly. One of the things they said was that comparing the two different metrics used by the Education Funding Agency, they found that the UDI criterion was more difficult to achieve than the Daylight Autonomy criterion. Usually if a space met the UDI, it was likely to meet the Daylight Autonomy as well. They felt that UDI actually changed their approaches to design. Instead of, as I was saying earlier, just chucking glazing at a problem, which, I mean, I don't know if you're familiar with school design, but it used to have quite high recommended daylight levels. So maybe 4% average daylight factor or going back 2% minimum daylight factor. And so there was a temptation always to have as much glazing as possible. For using the UDI, that didn't actually work because you get these areas near to the windows which had very high luminances. And so you'd need a more subtle approach which might include limited window areas but better uniformity, often by having higher ceilings and window heads, or by using roof lights, or with clear-story windows or windows in two sides of a room, maybe with a light well lighting the back of the room. And the useful daylight illuminance also encouraged designers to think about shading right from the outset. And one of the things that's always, as a daylight designer, one of the sort of tempting things is always to think, well, we'll control the sunlight later on, we'll think about shading later on. So you design this space with lots of daylight, and then you sort of compartmentalize out the shading, and you think, well, we'll worry about shading later. If it's too bright, we'll just do shading. Whereas the useful daylight illuminance, that encourages you to think about shading at the outset, because you've got to do this actually within your useful daylight illuminance calculation.
I can draw parallels with housing, although, as you said, some might be appreciated. But the heating criteria, always get to remember later on, we've got too much glass and we assume there's a nice mirrored Venetian blind below and if the sun's available, but the contractor doesn't install it and the information doesn't go to the user.
Yeah. Well, this is also a thing with these schools, because one of the things we found was we had a debate about how people model shading, and different consultants had different approaches to modelling shading. And some assume that, say, you just had a fixed shading, like an overhang or light shelf, which is a perfectly reasonable thing to do. Other people had more complicated sorts of shading based on, say, if it's above a particular light level. I think Chris was talking about this earlier on. Above a particular light level, then you get the blinds coming down.
So can you comment on that last point? From working in education myself, one thing where I think we're perhaps letting down the schools is the location, the use of the interactive whiteboards is not included when we're designing daylight. And then when you go in the schools, a lot of teachers, depending on where it ends up, that's when the blinds come down and they stay there.
Yeah.
So what we design isn't actually what we end up achieving.
That's right, that's a very good point, yeah. Did everybody hear that? Yeah. The other thing is that we talk quite a lot about calculation methods, and how you actually calculate these things in detail makes quite a big difference. The Education Funding Agency guidance required at the time, I don't know if this has changed since, because people were lobbying for them to change it, but at the time it required a 250 mil grid size, which is about 8 inches in it, 10 inches in old money. And that gives a lot of calculation points in a large space such as a gymnasium or school hall. But the bigger grid might end up overestimating the useful daylight luminance, because essentially if you've got a bigger grid, then your points are going to be further away from the windows and walls, and hence less likely to have a low UDI. And there was a gentleman talking earlier on about using an offset. That was you, wasn't it? You were talking about using an offset and excluding points close to the walls. And the Education Funding Agency allows this. It allows a 0.5 metre offset on the basis that children aren't going to be working really close to the walls. And this is quite a reasonable assumption, because of course you're not gonna have some poor kid actually sort of trying to read their school book or whatever really close to a wall. But it does make a big difference to the UDI, because of course you're excluding those points which have the lowest illuminances by the walls, and you're also excluding the points right by the windows which would have their highest illuminance. So the actual size of this offset makes a big difference to what you calculate. The time step also makes a difference. Although sometimes it's a bit of an artificial one, because these weather data, often they're hourly values, and so what happens is you get an hourly illuminance, and then an hour later you get a different illuminance, and those are averages over a whole hour. And so what happens is that these programs, when we're working this out, they have to interpolate between hours. And of course, that's not necessarily illuminance you actually get at that particular instant. It's just the something in between one hourly average and another hourly average. And this averaging process tends to increase the UDI, because you're taking out the very high daylight levels. While I've been speaking, the sun has been bombing up and down. You can't see it because you're all focused on me. But I can see the back of the room has been getting alternately brighter and lighter. And of course, that's all averaged out in this hourly irradiance or illuminance or thing you calculate for UDI. And so automatically, by using this sort of approach and this sort of time step, you're actually changing the UDI and probably overestimating it. And UDI also depends on the weather file used, and obviously if you've got sunnier locations, you might have daylight, the high level of daylight exceeded for more of the time. And one of the complaints that people had was that some weather data files were not reliable, and what would happen is that these, you'd be going through the weather data file and it would suddenly have a spurious data point with either a 0 or very high irradiance, and of course that messed up your UDI because it would automatically give really high or low values in the room. So accurate and reliable weather data were seen as essential.
Has anyone done any work looking at the different weather files? Because obviously in temperature terms, CIBSE and Met Office have been through a great deal of efforts trying to get average years and design peak years just on temperature, which has a number of parameters and other compromises. But actually the reliability of constancy between one year and another in light data is another factor which is being considered in whether it's a good year for data or not.
Yes. Yeah, I mean, this is an issue. And I think it's an issue that affects the sunlight perhaps more than the diffuse light. One of the things we found, we did a study quite a long time ago, and one of the things we found was that diffuse daylight within the UK, this is not sort of elsewhere, it tended to be more just a function of latitude rather than sunny the place was, because if you get really sunny skies, they tend to be sort of dark blue and not so bright. And overcast days tend to be not so bright, and really it's the skies in the middle that tend to be brighter, and just purely in diffuse daylight terms. So the diffuse daylight doesn't actually vary so much according to climate, whereas the sunlight does. And of course the sunlight doesn't really affect the daylight autonomy, but it does affect useful daylight illuminance. Okay, right, well I'm going to have sort of taken a bit longer than I was hoping to, but I'm going to hand back to Cosmin now, belatedly, and he's going to tell you a bit about some more of the calculations we did.
Okay, so basically in this phase of the project, we used the same example rooms as those used previously when we calculated Lenny, and we used these rooms in DaySim. So we calculated daylight using DaySim 3.1 under Ecotect as well. That's a table which presents the various room sizes, types, and daylight opening sizes. We considered, for these calculations, we considered 3 sizes of glazed area. So we had small glazed area, intermediate, and large. And for intermediate glazed area, we had, again, 2 subsets, say, single opening and multiple openings for the large rooms only. For the small rooms, we only had 1 opening. And the reason for that was purely to look at how that would affect daylight uniformity across the space. Obviously, if you have multiple openings, daylight is a bit more uniform than having 1 single opening, which also may be a bit unrealistic, to be honest. Again, we consider the same external obstruction scenarios for the side-lit rooms and no obstruction for top-lit rooms, working plane grid 80 centimeters above the floor, and in this case we consider an offset distance of 0.5 meter from the walls, and that's the grid spacing for the large rooms and small rooms. So, okay, we use the default radiance and DaySim settings, including occupant behavior, and we looked at 3 occupancy types, school and office, with 2 different usage times, so 8:30 to 5:30 and 6 to 6. We used the weather file for London, and we considered both 300 lux and 500 lux minimum illuminances. That's, say, the input data. And what we wanted to determine was this list of parameters. So first we wanted to see what the average daylight factor was across the working plane, and then daylight autonomies for 500 and 300 lux across the working plane, average UDI across the working plane, and in this case we just used the default values in DaySim. So you can see 2000 lux instead of 3000 as per the EFA document. We also looked at the spatial daylight autonomy, and because we considered that it is relevant to look at the ends of luminary rows, which basically is more realistic to consider if you want to determine the energy savings for lighting systems that use photoelectric controls. We also calculated the point values for the daylight factor, the DAs and UDIs at luminary row ends. And these ends were considered at half a meter away from the side wall. You can see this diagram here showing what those ends, where those ends were. And in case those points didn't match the points on the grid, we just interpolated the values for the grid points that were closest to those row ends. Yeah, so basically that's the reason why we chose to look at those luminary row ends as well, because we had this hypothesis that percentage saving from an on-off photoelectric control system, which switches each row of luminaires separately, would be the same with the average of the daylight autonomies at the end of the rows. So that's why we calculated the point DAs at the ends of these luminary rows. And then we compared the average daylight autonomy and the UDI autonomous across the working plane to each other and with the average daylight factor. We also average, as I already mentioned, the point DAs for luminary row ends, and this average and the average daylight autonomy across the working plane, we compare them with the so-called area-weighted dependency factor, daylight dependency factor, as given by the European standard. And purely because we wanted to see how, the relationship between these values in order to see whether there are differences in terms of predicting energy savings by the two methods. And we'll see the results in the next slides. I'm not sure if you can see this very well. We just try to represent the various findings, lots of data again, within these few slides. These graphs here show DA 500 and average daylight factor. Just to make this clear, these findings here refer to the scenario of an office application for the hours 8:30 to 5:30, and also for 500 lux maintained illuminance. This is what we're going to see in the next slide. Sorry.
ADF calculated by the average of the daylight factors across the working plane or with the formula?
No, we calculated these values only using DaySim. So that's all computer-based daylight modeling. Right, so these graphs, again, DA 500 against ADF, and it can be seen that there is, all these dots here represent all the scenarios with different obstructions, different facade orientations, so there are many points there. The thing is, you can see it's a bit difficult to get the DA 500 above 50%. And there were just a few cases where this happened. It's not very visible, so 50% is, 50% is somewhere here. So you can see and this happened for the large room having the widest windows. So only in those cases, and also facing south, only in those cases it is possible to get DA above 500 above 50%, and that corresponding to high daylight factor values. It's not very visible here, but it was in the region of 4%, say 3 to 4%. Something similar happened for the small room with higher daylight average daylight factor values, 4 to 5%. In the rest of the scenarios, it was quite difficult to get the DA 500 with about 50%. And there is also, ADF doesn't vary obviously with the orientation. It does vary with the glazed area, the same daylight autonomy, but there's also differences in DAs, obviously, depending on the orientation. There isn't much variation in terms of the top lit rooms, but the same findings would apply in this case as well. This is UDI autonomous versus ADF, so something similar can be seen here. It is, however, quite difficult to see to achieve UDI above 80%, although we should be mentioned that as already explained earlier, this UDI autonomous was based on 2,000 lux rather than 3,000 lux. So obviously there's a difference there. But even so, you can see there are differences between the various scenarios. And this graph shows UDI autonomous versus DA 500. Sorry.
Can I just clarify? Is your average daylight factor, is that a mean average of all the points in the room?
Yes. That's the average of all the points on the grid, that grid used for both rooms.
And that is, just to clarify, that is the default that Damesim provides anyway. That's the number that you are using.
Sorry, the daylight factor you mean?
Damesim, whenever it simulates results, it gives you the average daylight factor anyway. That's the number you're using?
Yeah.
Okay.
But you can also get the point values.
Yes, correct.
And
So
basically
you know
what,
the average, that's all.
yeah, we just took those point values and averaged them across the whole working plane. I mean, the whole grid, basically. Right, UDIA versus DA 500. Again, it's this graph here shows that it's a bit easier to achieve higher UDI A values compared to DA 500 for all the cases investigated. And again, they have all these differences between the various scenarios. And what's interesting to see, basically, these graphs in the next slides will refer to say the potential energy savings for lighting. And in order to assess this aspect, we compared the daylight autonomy, as mentioned earlier, the average value of the daylight autonomy 500 across the working plane against this value. Actually is 1 minus FD 500, say. So that's the daylight dependency factor given by the European standard for 500 lux maintained illuminance. And the reason why we used 1 minus that value, or 100% minus that value expressed as a percentage, was purely to have a similar, say, trend in both parameters. Because obviously they are inversely proportional, say, daylight dependency factor and DA. That's why we use that formula. And
Can you remind us what hours a day, the day hours there are?
yes, it was 8:30 to 5:30, for an office application. Okay, so it's interesting to see that for the large room, which is on the top graphs, the European standard, say, method tends to underestimate the daylight availability. So, in a way, it overestimates the energy used for lighting, both in the current version of the standard and in a newly proposed standard. Whilst for the small rooms, the situation was completely different. It was the other way around. So you have higher prediction of daylight availability using the European standard method compared to the DA. And that's for the average daylight autonomy across the working plane. If we look at that was for the side lit rooms, and that's for the top lit rooms, where the situation is different. So you have an overestimation of daylight availability using the EN method for the large rooms, and it's the other way around for the small rooms in both versions of the standard. As regards comparing the same value, say 1 minus FD, against the DA 500 rows, which means the average of the DA 500 values, point values, achieved at the ends of the luminary rows. We had 5 points for the large room and 3 points for the small room. models. That's the DA500 rows value. So if we compare this, I mean, basically the idea is that in real applications, it's more common, say, to switch on-off luminar rows separately, but as a continuous row, rather than switching individual luminars on-off. You know, each one having its own sensor, its daylight sensor. Which method of using, say, one sensor per luminaire rather applies in the other method of using the average DA 500 across the whole working plane. So that's the difference there. We considered it being more realistic to look at DA 500 rows values. And using this principle, it was interesting to note that the situation changes a bit in that the daylight availability predicted by the EN method is higher. So in a way, this method, the EN method, overestimates the daylight availability in all cases, in most cases, say, most of them, both in the current and in the draft version of the standard. That's for the side lit rooms, and that's for the top lit rooms, where a similar tendency applies. So, yeah, I mean, these graphs show the same things, but represented differently. The FD and the DA 500 values, average and at luminar row ends, were represented together against the glazed area. We had 4 scenarios of glazed area for the large rooms and 3 for the small rooms. We'll see that in the next slide. As I mentioned earlier, 1 is small glazed area, 2 is intermediate but single opening, 3 is intermediate with multiple openings, and 4 is large glazed area. In dotted line, you can see the FD 500 values and the continuous lines DA 500 values. I think that's, yeah, it's just the DA 500 rows, so at the ends of the rows. So what can be seen in these graphs as a common trend is that in most cases, FD base prediction is higher than the DA 500 rows prediction. And the same applies in the case of small rooms, where again you have small glazed, intermediate glazed, and large glazed areas. And this is for the top lit rooms as well. For large rooms, the same thing, the same finding applies. For the small room, there are some differences depending on the size of the glazed area. And the thing is that, for example, with small rooms, it may be that some points are further away from the opening, that their DA 500 is too low. I mean, it can't be achieved at all. Right, so this slide summarizes these findings on climate-based daylight modeling for our example rooms. And in short, it can be said that daylight availability using the European standard varies in steps, whereas daylight availability predicted by using the daylight autonomy method varies progressively with glazing area and orientation. So again, something similar to what Lenny showed earlier can be also noticed in this case. However, the proposed version of the European standard produces more or less similar results, but you have this additional thing of taking into account the facade orientation. So you have changes in daylight prediction based on this. In general, the European standard underestimates daylight availability based on the average daylight autonomy in large sided rooms, and generally overestimates it in small sided rooms. And the reverse applies for the top lit rooms. So there is some variation here. However, by looking only at the daylight availability predicted using the average daylight autonomies at luminary row ends, which is what we would expect in a real application, both the current and the newly proposed version of the European standard overestimate daylight prediction in most cases. So this leads to an underestimation of the energy used for electric lighting. So this is something which would need to be considered, we would say. And yes, so I'm going to give Paul.
Yeah, I just wanted to sort of wind everything up by taking us right back to the start and thinking about why are we doing this stuff in the first place, and then to say, well, to think about, well, you know, should we be using a climate-based approach? If we take our things in the order we took them before, loss of light to existing buildings is quite difficult to assess using climate-based daylight metrics. If you're using the useful daylight elements, you could conclude that it's actually a good thing to block somebody's light, because then you might be reducing the UDIE, these very high luminances, which somebody in a house might actually like to have, but which your new big skyscraper is blocking. So you could actually, it's quite, and if you're using this daylight autonomy in the middle of a room, that's quite a difficult thing to do, because what might be happening is you might actually take all the daylight from the rear of somebody's room. What tends to happen if you have a new obstruction go up outside is it tends to affect the rear of the room first. And you could be taking all the daylight away from the rear of the room, but not really affecting the middle of the room all that much. So it's difficult to use these metrics for loss of light. For daylight provision in housing, I'm quite concerned about the new European standard based on daylight autonomy, because it seems that the illuminances that are being used there, the 300 lux, are too high generally for housing. And also that for housing in urban areas, it may well be impossible to meet these daylight autonomies, even the minimum ones which are in the European standard. And so we could end up seeing an abandonment of daylight calculations for housing in if the new European standard is replaced by replaces the existing British standard BS 8206 Part 2 with its average daylight factor recommendations. And I think that would be a bad thing, because one of the things that the BS does, I mean, it doesn't always give you great daylight, but what it tends to do is to weed out the really sick buildings, the buildings with average daylight factors of 0.1. I'm concerned that with the new European standard, then you could get a situation where those people say, well, you know, everything fails the European standard, so it's no worse than anything else. And we can also use, well, not necessarily the exact metrics, but the numbers that we generate in order to give us daylight exposure for things like art galleries and grass growth. I missed out the BREEAM and LEED credits. There's a case in calculating credits for BREEAM. Often people miss out the daylight credit because it's too complicated. And that's a bit of a shame, especially because they're using a quite simple average daylight factor calculation. So there's a danger if it went over to compulsory climate-based daylight metric, but people wouldn't just wouldn't bother with the daylight credit at all because of the increasing complexity of climate-based calculation. So finally, climate-based daylight modelling can allow for the effects of orientation and sunlight. The daylight autonomy can be related to electric lighting use. The useful daylight illuminance allows shading to be considered as an integral part of our daylight calculation. As I've argued, it's less suitable for domestic interiors where you might want quite high daylight levels, and the calculations are a lot more complex. I'll just leave this slide out. Our project report was intended to be available on the CIBSE Knowledge portal, and I checked yesterday, and it still hadn't been made available, but they've told me that it has now been made available. So hopefully, if you follow this link, which is given on the end slide, you'll be able to download our entire project report, which is over 100 pages, and it's got a lot more of those graphs that Cosmin showed you. So. Essential bedtime reading, I guess. So that's all we were going to say, but if you have questions or comments, now's the time. I think we can go on till about 4:30.